Welcome to the deep dive. Today we're tackling a really big one, carbon and its compounds. This chapter, it's absolutely crucial, isn't it, for board exams and definitely for competitive tests like JE and NEET. I'm really keen to get into this.
Absolutely. It's great we're focusing on this. Carbon is, well, it's fundamental. We're not just talking about exam points here, though it's obviously key for that.
Right.
We're talking about understanding the actual building blocks of, well, pretty much everything around us, life itself.
Yeah, it seems to be everywhere.
Exactly. So in this deep dive, we'll unpack why carbon is so special, look at its unique way of bonding, and figure out how it manages to form, literally millions of different compounds, right down to the chemistry of, say, soap.
Okay.
Our goal is simple.
Yeah.
Make every concept crystal clear, step by step. Really lay the groundwork for your exam success. So let's jump in.
Great. So where do we start? Carbon's importance seems obvious. Like you said, it's everywhere.
Let's start right there. It's ubiquity. Carbon is the basis for all living organisms. Everything from the simplest bacteria to, well, us. And beyond life, think about the materials we use constantly.
Like what sort of things?
Okay, try this little mental exercise like Activity 4.1 suggests.
Yeah.
Just list maybe 10 things you've used since you woke up this morning.
Okay. Food, clothes, maybe medicine, books, petrol or diesel in a car or bus.
Perfect. See?
Ah.
Food, clothes, medicines, books, fuels, most of those, probably all of them, are carbon-based compounds. It really is the foundation.
Right. That makes total sense. Carbon sounds vital. But I remember reading something in the source material that seems a bit weird. It says carbon isn't actually that common in the Earth's crust or the atmosphere. It feels like a contradiction.
Ah, that's a fantastic point to bring up. It really highlights a key paradox about carbon. You're right. It does seem contradictory at first glance.
Yeah.
Despite its immense importance, its sheer versatility, its abundance in the non-living parts of the planet is, well, surprisingly small. Let's look at the numbers. The Earth's crust, it contains only about 0.02% carbon. That's a tiny fraction. And it's mainly locked up in minerals. Think carbonates like limestone or hydrogen carbonates. Plus, of course, in fossil fuels like coal and petroleum.
Wow, 0.02%. That's really low.
It is. Now look at the atmosphere. It's even less in a way. Only about 0.03% of the atmosphere is carbon, and that's almost entirely in the form of carbon dioxide gas.
So hang on. It forms the basis of all life, and we use it in countless materials, but it's barely there in the crust and air. How does that work?
It's not a contradiction, but actually proof of carbon's incredible properties. It's these unique properties that allow it to form such stable, diverse structures and to be recycled so efficiently through things like the carbon cycle, even though the raw amount isn't huge.
Okay, so it's not about quantity, but quality. It's special abilities.
Exactly. Think of it like a master key. You only need one, but it can unlock countless doors. Carbon's scarcity just makes its role in biology and technology even more remarkable. And that leads us perfectly to the next big question. What are these special properties? What makes carbon so unique?
Right, let's get into that. What makes it tick?
Okay, to understand carbon, let's first quickly remember what we know about other types of compounds, specifically ionic compounds. We covered those before, right?
Yeah, formed by transferring electrons, like sodium chloride.
Exactly. And what were their typical properties? High melting points, high boiling points.
Right, it takes a lot of energy to melt them. And they conduct electricity, but only when dissolved or melted.
Perfect recall.
Yeah.
High melting boiling points because of those strong electrostatic attractions between the ions. And they conduct electricity only when the ions are free to move in solution or molten state.
Got it.
Now let's contrast that with most carbon compounds. Take methane, CH4, as an example.
Okay.
Simple gas used as fuel. Its melting point is incredibly low, around 90 Kelvin. That's minus 183 Celsius. And its boiling point is about 111 Kelvin, minus 162 Celsius.
Wow, okay. That's vastly different from ionic compounds.
Vastly different. This tells us straight away that the forces between methane molecules must be very weak. It doesn't take much energy at all to pull them apart.
So intermolecular forces are weak.
Precisely. And what about conducting electricity? Try passing a current through methane gas or most liquid carbon compounds like ethanol. They're very poor conductors.
Ah, okay. So weak forces between molecules and poor conductors. What does that imply about their bonding? No ions.
Exactly. The bonding in these compounds doesn't seem to create free-moving ions. If there are no charged particles to carry the current, then they won't conduct electricity. This points away from ionic bonding.
So if they don't form ions by gaining or losing electrons, how do carbon atoms bond? I remember carbon has 4 valence electrons in its outer shell. So does it try to gain or lose them somehow, even if it's difficult?
That's the million-dollar question. And yes, you're spot on. Those 4 valence electrons are the absolute key. Let's break down carbon's situation. Atomic number 6.
Right. 2 electrons in the first shell, 4 in the second.
Correct. K shell has 2. L shell, the valence shell, has 4. Now, to get stable, like a noble gas, it ideally wants a full outer shell, usually 8 electrons, the octet rule.
Okay.
So with 4 valence electrons, carbon faces a dilemma. 2 theoretical options, but both are problematic.
Problematic how?
Well, option 1, it could try to gain 4 more electrons to form a C4 ion. Imagine that. You'd have a nucleus with just 6 positive protons trying to hold on to 10 negative electrons.
That sounds crowded and unstable.
Extremely unstable.
Right.
The repulsion between those 10 electrons would be huge, and the 6 protons just wouldn't have enough positive charge to keep them all tightly bound. It's energetically very unfavorable.
Okay, so gaining 4 is out. What about losing them?
That's option 2. Lose all 4 valence electrons to form a C4 plus concation. But think about the energy involved. Removing even 1 electron takes energy. Removing 4.
A huge amount of energy.
An enormous amount. Each time you pull an electron away, the remaining ones are held even more tightly by the nucleus. It gets progressively harder. And you'd end up with a tiny C4 plus ion 6 protons holding just 2 electrons. Again, highly unstable, requires way too much energy.
So it can't easily gain 4 and it can't easily lose 4. What does it do then?
It finds a brilliant compromise. Instead of transferring electrons, carbon shares its valence electrons with other atoms.
Sharing. Okay.
And it's not just carbon. Many other elements do this too. When atoms share electrons, those shared electrons effectively count towards the outer shell of both atoms involved.
So both atoms get to feel like they have a full shell.
Precisely. It allows both atoms to achieve that stable, noble gas configuration without needing to form ions, which avoids those energy problems we just discussed. This sharing creates what we call covalent bonds.
Covalent bonds. Okay, can we look at some examples? Make it clear.
Absolutely. Let's take it step by step with simple molecules you definitely know. Think of each shared pair of electrons as a bond, like a link holding the atoms together.
Okay.
First, hydrogen gas, H2. Simplest element. Atomic number 1, so just 1 electron. It needs 1 more to fill its first shell, like helium.
Right.
So 2 hydrogen atoms come close, and each shares its single electron with the other. They form 1 shared pair. This shared pair now belongs to both atoms.
So each hydrogen effectively has 2 electrons.
Exactly. Each achieves the stable helium configuration. We represent this single shared pair, this single covalent bond with a single line, HH.
Got it. Simple enough?
Think of it like this. Imagine you have the frame and handlebars of a bicycle, and your friend has the 2 wheels. Neither of you can ride alone. But if you share your parts, you build 1 complete, stable bicycle that both of you can use. Atoms share electrons similarly to become stable.
Nice analogy. Okay, what about something a bit more complex, like oxygen?
Good one. Oxygen gas, O2. Atomic number 8. Configuration is 2 electrons in the K shell, 6 in the L shell. How many more does it need for an octet?
It needs 2 more. 6 plus 2 is 8.
Right. So when 2 oxygen atoms bond, each atom contributes 2 of its valence electrons to be shared. This means they form 2 shared pairs between them.
2 shared pairs, so a double bond.
Exactly, double bond. We draw it with 2 lines. O. This double bond allows each oxygen atom to complete its octet.
Okay. Single bond for hydrogen, double for oxygen. What about nitrogen?
N2. Let's see. Nitrogen N2, atomic number 7. Configuration is 2, 5. How many more does it need?
5 in the outer shell. Needs 3 more.
Perfect. So each nitrogen atom shares 3 of its valence electrons with the other nitrogen atom. This forms 3 shared pairs.
A triple bond. Then.
Precisely. A triple bond, very strong bond, makes nitrogen gas quite unreactive. Again, each nitrogen achieves its stable octet this way.
Okay, the sharing makes sense. H2, O2, N2. Now back to carbon. How does methane, CH4, fit in?
Right, methane, CH4. The classic example. We know carbon is tetravalent. It has 4 valence electrons and needs to form 4 bonds. And hydrogen, as we saw, has valency 1, needs 1 bond.
So carbon needs 4 partners, and there are 4 hydrogens.
Exactly. The central carbon atom shares 1 of its valence electrons with each of the 4 hydrogen atoms. And each hydrogen shares its single electron back with carbon.
So 4 separate single bonds, CH bonds.
Yes, 4 single covalent bonds are formed. This neat arrangement satisfies carbon's octet, is sharing in 4 pairs, total 8 electrons, and each hydrogen's duplet, each shares 1 pair, total 2 electrons. A very stable molecule.
Okay, that clarifies the bonding. So just to recap the properties of these covalent compounds.
Good idea. Key takeaways. The covalent bonds within the molecule like this CH bonds in methane, are very strong. But the forces between different molecules, intermolecular forces, are generally weak.
Which explains the low melting and boiling points we saw earlier.
Exactly. And because electrons are shared, not transferred, there are no free ions formed.
So they are poor conductors of electricity.
Correct. No mobile charged particles means poor electrical conductivity. These are fundamental differences compared to ionic compounds, really crucial for your exams.
Got it. Strong bonds inside, weak forces between, no free ions, poor conductivity.
Yeah.
Makes sense. Now, you mentioned earlier that carbon exists in different forms, like diamond and graphite.
Ah, yes. Now things get even more interesting. This phenomenon is called allotropy. It's where the same element, in this case carbon, can exist in different structural forms in the same physical state, and these forms have distinctly different physical properties, even though chemically they are still just carbon.
So diamond and graphite are allotropes of carbon. They seem worlds apart. One is super hard and sparkly, the other is soft and gray.
Exactly. Perfect examples. Their differences are stark, and it all comes down to how the carbon atoms are bonded and arranged. Let's look at diamond first.
Okay.
In a diamond crystal, picture each carbon atom forming strong covalent bonds with 4 other carbon atoms. These bonds point outwards tetrahedrally, creating a rigid, interconnected, three-dimensional network structure.
Like a very strong repeating scaffold.
Precisely. An incredibly strong interlocking framework extending throughout the crystal. This structure, where every atom is tightly locked in place by strong bonds, is what makes diamond the hardest known natural substance.
Hence its use in cutting tools, not just jewelry.
Right. And labs can even make synthetic diamonds by mimicking the high pressure and temperature found deep in the earth where natural diamonds form. They're small, but structurally identical.
Okay, so diamond is a 3D network, 4 bonds per carbon, super hard. What about graphite? How is it so different?
Graphite is fascinatingly different. In graphite, each carbon atom bonds strongly to only 3 other carbon atoms. Yeah. And crucially, they all lie in the same flat plane.
3 bonds, but carbon needs 4.
Good question. It satisfies its valency because one of those 3 bonds is actually a double bond, so each carbon still effectively forms 4 bonds. These bonded atoms form flat sheets of interconnected hexagonal rings, like a layer of chicken wire or honeycomb.
Okay, flat sheets of hexagons.
Yes. And then, these flat layers are stacked on top of each other. But the forces between the layers are much weaker. Think of stacking sheets of paper.
Ah, so the layers can slide over each other easily.
Exactly. That layered structure with weak interlayer forces is what makes graphite feel smooth and slippery. That's why it's used as a lubricant, and of course, it's the lead and pencils layers slide off onto the paper as you write.
Right. But wait, you also mentioned graphite conducts electricity. Most nonmetals don't. How does that work?
Another excellent point, and vital for exams. Unlike diamond and most nonmetals, graphite is a very good conductor of electricity. The reason lies in those double bonds within the hexagonal layers.
The extra electrons in the double bonds?
Precisely. Those electrons aren't fixed between just 2 atoms. They are delocalized, meaning they are free to move along the entire layer or sheet.
Like mobile charge carriers?
Yes, they can easily move throughout the layers, carrying electrical charge. This mobility of electrons is what allows graphite to conduct electricity so well, unlike diamond, where all electrons are locked in strong single bonds.
Fascinating difference. Same element, completely different electrical properties due to bonding.
It really is. And we should briefly mention a third major class of allotropes, fullerenes, discovered more recently. The most famous is C60, Buckminster fullerene.
C60, like a football shape.
Exactly like a soccer ball.
Yeah.
60 carbon atoms arranged in a spherical structure made of hexagons and pentagons, named after Buckminster Fuller, the architect known for geodesic domes, which look similar. Fullerenes opened up whole new areas like nanotechnology.
Wow, okay. So the key takeaway for allotropes is it's all about the arrangement.
Absolutely. It's how the carbon atoms are bonded together, the structure that dictates the physical properties.
Yeah.
Diamond's 3D network versus graphite's layers versus fullerene spheres. Same element, different structures, vastly different properties.
Got it. Diamond, graphite, fullerenes, different arrangements, different properties. Now, let's connect this back. You said carbon forms millions of compounds, far more than any other element. Why?
Yeah.
What gives it this incredible versatility?
That's the core question, isn't it? This phenomenal ability stems directly from the nature of his covalent bonding, specifically from 2 key properties we need to understand thoroughly.
Is one of them that ability to bond with itself? You mentioned strong carbon bonds.
You're right on track. The first major factor is indeed catenation. That's the term for carbon's unique and remarkable ability to form strong, stable bonds with other carbon atoms.
Self-linking.
Exactly. And because these CC bonds are so strong and stable, carbon atoms can link up to form incredibly large and diverse molecules. We're talking long, straight chains.
Like beads on a string.
Yes, or branch chains like the branches of a tree. And they can even loop back on themselves to form rings.
Chains, branches, and rings. Okay.
And within these structures, the carbon atoms can be linked by single, double, or triple bonds, adding even more variety.
So catenation allows for huge structural diversity.
Huge diversity. And this leads to the distinction between saturated and unsaturated compounds again. If a compound has only single bonds between carbon atoms, it's saturated.
Like alkanes.
Correct. If it contains one or more double or triple bonds between carbon atoms, it's unsaturated.
Alkenes and alkynes.
Now, to appreciate how special carbon's catenation is, let's briefly compare it to silicon, which is just below carbon in the periodic table. Silicon also has 4 valence electrons.
So shouldn't it also form chains?
It does, but only to a very limited extent. Silicon can form chains with hydrogen, but they typically only reach up to 7 or 8 silicon atoms long. And importantly, these silicon chains are quite reactive. They break down easily.
Whereas carbon chains can be massive and stable.
Exactly. The carbon bond is exceptionally strong and stable, allowing for chains of hundreds or even thousands of atoms. Think about complex biological molecules like DNA or proteins or polymers like plastics. That stability is key. It's why carbon forms the backbone of life in organic chemistry.
Okay, so catenation's number one. What's the second factor for carbon's versatility?
The second factor is its tetravalency. We keep coming back to this, but it's fundamental. Carbon has a valency of 4.
Meaning it can form 4 bonds.
Right. It's capable of bonding with 4 other atoms simultaneously. As we saw with catenation, these can be other carbon atoms. But crucially, carbon also readily forms strong, stable bonds with atoms of many other elements.
Like hydrogen, oxygen, nitrogen.
Exactly. Oxygen, hydrogen, nitrogen, sulfur, chlorine, the halogens, a whole host of elements. When carbon bonds with these other elements, we call them heteroatoms when they replace hydrogen in a hydrocarbon framework, it creates compounds with specific properties. These properties are often largely determined by the non-carbon elements present.
So the combination of linking to itself, catenation, and linking to 4 other atoms, including different elements, tetravalency, creates almost limitless possibilities.
Precisely. Limitless combinations and structures. And there's one more reason why these bonds, both CC and C other element, are so strong. It's carbon's small size.
How does size matter here?
Being a small atom means its nucleus, which holds the positive charge, is relatively close to the shared electron pairs in the covalent bonds. This allows the nucleus to exert a strong pull, holding onto those shared electrons very tightly.
Ah, like a strong grip.
Exactly. Bonds formed by larger atoms, where the nucleus is further away and shielded by more inner electrons, tend to be weaker. So carbon's small size contributes significantly to the strength and stability of its compounds.
Catenation, tetravalency, and small size leading to strong bonds, that really paints a picture of why it's so versatile.
It does. And maybe a quick historical note here is interesting. For a long time, scientists believed that carbon compounds called organic compounds could only be made by living things. They thought a special vital force present only in organisms was needed.
Vital force theory.
Yes. But that idea was completely overturned in 1828 by Friedrich Wöhler. He managed to synthesize urea, an organic compound found in urine, from an inorganic starting material, ammonium cyanate, in his lab.
So no vital force needed after all.
None at all. It proved organic compounds could be made artificially, opening the floodgates for synthetic organic chemistry. But even today, the vast field studying carbon compounds, with a few exceptions like oxides and carbonates, is still called organic chemistry. A legacy of its origin in studying life.
Pretty much. Now, shall we start building up some of these compounds systematically? Look at how chains grow and branch.
Yes, please. Let's start simple and build up. We had methane, CH4. What's next?
Okay, let's go step by step. After methane, 1 carbon, comes ethane, C2H6. To draw it, first link the 2 carbons with a single bond, CC.
Right.
Each carbon needs 4 bonds total. It's already got 1 bond to the other carbon. So how many more does each need?
3 more bonds each.
Correct. And we have 6 hydrogens available. So we attach 3 hydrogens to each carbon atom. H3C, CH3. All single bonds.
So ethane is saturated.
Yes, fully saturated. Now, what if we have only 4 hydrogens for 2 carbons, C2H4?
Okay, CC. Each carbon needs 3 more bonds, but we only have 4 hydrogens.
Yeah.
That doesn't work with just single bonds.
Exactly. To satisfy the valency, the two carbon atoms must share more electrons between themselves. They form a double bond.
CC.
So H2C, CH2, that's ethene.
Precisely. Each carbon now forms a double bond with the other carbon and single bonds to two hydrogens. Total 4 bonds for each. And because it has a double bond, ethene is.
Unsaturated. And you said unsaturated compounds are generally more reactive than saturated ones?
Absolutely critical point. Yes, unsaturated compounds like ethene are generally more reactive. That double bond is a site of higher electron density and can open up to add other atoms.
Okay. What about C2H2, even fewer hydrogens?
Ethene, 2 carbons, only 2 hydrogens. How do we make that work?
Well, if a double bond worked for ethene, maybe a triple bond here.
You got it. A triple bond between the carbons. HgCH. Each carbon forms a triple bond to the other carbon and a single bond to one hydrogen. Again, 4 bonds per carbon are satisfied. Ethene is also highly unsaturated and reactive.
Saturated like ethene versus unsaturated like ethene. And unsaturated means more reactive. Key difference.
Absolutely fundamental. Now let's talk structures. We've seen simple chains. Methane, ethane, propane, 3 carbons, butane, 4 carbons, pentane, 5, hexane, 6. These are often called straight chains, though they're actually zigzagging in 3D.
Okay, but chains aren't always straight, right? They can branch.
Yes. And this leads to a really important concept, structural isomers.
Isomers, same formula, different structure.
Exactly. Compounds with the identical molecular formula, same number and type of atoms, but different arrangements of those atoms in space. Let's take butane, C4H10.
Okay, 4 carbons, 10 hydrogens.
You can arrange the 4 carbons in a straight line.
Yeah.
CH3, CH2, CH2, CH3. We call this N-butane, normal butane.
Right.
But you can also arrange them differently. You could have a central carbon bonded to 3 other carbons with hydrogens filling the rest. CH3-CH3, CH3, CH3. This is called isobutane, or more systematically, 2-methylpropane.
So both are C4H10, but the atoms are connected differently.
Precisely. Same formula, different structure, and they actually have different physical properties, like different boiling points. Isomerism is a huge reason why there are so many carbon compounds.
Branches create isomers. What about rings?
Carbon is great at forming rings, too. You can have saturated rings like cyclohexane, C6H12, 6 carbons in a ring, each bonded to 2 hydrogens, all single bonds within the ring.
Okay, a saturated ring. Can rings be unsaturated?
Definitely. The most famous example is benzene, C6H6, 6 carbons in a ring, but with alternating single and double bonds, though the reality is a bit more complex with delocalized electrons. Benzene is a cornerstone of organic chemistry.
Wow, chains, branches, rings, single, double, triple bonds. It really builds up complexity quickly.
It does. And to keep things organized, we have classifications. Compounds with only carbon and hydrogen are hydrocarbons.
Right, and within hydrocarbons.
We have the main families. Alkanes, saturated hydrocarbons, single CC bonds only. General formula, CnH2n plus 2. Alkenes. Unsaturated contain at least 1 CC double bond. General formula CnH2n. Alkanes. Unsaturated contain at least 1 CaC triple bond. General formula CnH2n danger.
Those general formulas seem really useful for exams.
They are vital. Now, carbon doesn't just bond with hydrogen, it bonds readily with other elements too. This brings us to heteroatoms and functional groups.
Okay, what's a heteroatom?
It's basically any atom in an organic molecule that isn't carbon or hydrogen. Think oxygen, nitrogen, sulfur, halogens, chlorine, bromine, etc. When one of these replaces a hydrogen atom in a hydrocarbon chain, it's called a heteroatom.
And these heteroatoms create functional groups.
Often, yes. A functional group is a specific atom or a group of atoms, including heteroatoms, within a molecule that is responsible for the characteristic chemical reactions of that molecule. It's the active part.
So the functional group dictates the chemistry regardless of how long the carbon chain is.
Largely, yes. It gives the molecule its chemical personality. Let's look at the main ones from Table 4.3. Haloalkanes have a halogen, like NaCl or NaCbr attached, named with prefixes. Chloro, bromo, example. Chloropropane, alcohols, contain the AQH hydroxyl group, named with suffix. Example, propanol, aldehydes, have a GO group at the end of a chain. Suffix, HSL. Example, propanol, ketones, have a CO group within the chains. Suffix having 1. Example, propanone. Carboxylic acids contain the AGHH group at the end. Suffix, cetoic acid. Example, propanoic acid.
Okay, so NaCl-OH, CHO, CuO-COH. These are the key functional groups dictating properties.
Exactly. Recognizing these functional groups and knowing their general properties is absolutely essential.
This leads nicely into the idea of a series of compounds with the same functional group, right? The homologous series.
Perfect transition, yes, the homologous series. Imagine you take one functional group, say the HEH group for alcohols, and you attach it to carbon chains of increasing length.
Like methanol, CH3OH, ethanol, C2H5OH, propanol, C3H7OH.
Precisely. That sequence forms a homologous series. They all share the same functional group, OH, and therefore have similar chemical properties.
So what's the pattern connecting them? How do they differ?
The key defining pattern is that each member differs from the next one by exactly a CH2 unit.
CH2, so one carbon and two hydrogens.
Yes. Go from methanol to ethanol, you add CH2. Ethanol to propanol, add another CH2. It's a constant difference.
And does that mean a constant difference in mass, too?
Absolutely. Carbon has a mass of 12U, hydrogen 1U. So a CH2 unit has a mass of 12 plus 2, 1, equals 14U. Each successive member in a homologous series has a molecular mass exactly 14U greater than the previous one.
14U difference. That sounds like a classic exam question.
It very often is. And remember those general formulas we mentioned, like CnH2n plus 2 for alkanes? Each homologous series can be represented by such a formula. Alcohols, for example, can be represented as CnH2n plus 1OH.
Okay, so same functional group, differ by CH2, mass difference of 14U, general formula. What about their properties?
Physical properties show a gradation. As the carbon chain gets longer and the molecular mass increases, things like melting point and boiling point generally increase.
Why?
Because the intermolecular forces, van der Waals forces, become stronger between larger molecules, so it takes more energy to separate them. Solubility might also show a trend.
But chemically, you said they are similar.
Yes, their chemical properties remain very similar throughout the series. Why? Because the chemistry is dictated by the functional group, and the functional group is the same for all members. This is a huge simplifying principle in organic chemistry.
Okay, that makes studying them easier.
Perfect.
Now, naming, with millions of compounds, how on earth do we name them systematically?
Nomenclature. It seems daunting, but there's a very logical system, the IUPAC system, that allows us to give a unique name to almost any compound. Let's break down the steps.
Please do, step by step.
Step 1. Find the longest continuous carbon chain. This gives you the parent or root name. We use prefixes, meth1C, eth2C, prop3C, but 4C, pent5C, hex 6C, and so on. If the chain is saturated, the ending is -ane. So a 3-carbon saturated chain is propane.
Okay, find the longest chain, get the root name ending in -ane.
Step 2. Identify any functional groups. Are there any double, triple bonds, any heteroatoms or groups like OH, COH?
Right.
Step 3. Indicate the functional group. This is usually done with a prefix before the root name or a suffix after the root name, as we saw in Table 4.4. For example, Cl used the prefix chloro, while OH uses the suffix ol.
Okay, prefix or suffix?
Step 4. The vowel rule for suffixes. This is important. If the suffix for the functional group starts with the vowel, A-E-I-O-U, you drop the final E from the parent alkane name before added the suffix.
Example.
Okay, take a 3-carbon chain with an alkyl group, OH. The suffix is ol. Since O is a vowel, drop the E from propane. Propane plus ol, propanol.
Ah, okay. What if the suffix starts with a consonant?
Then you keep the E, though most common suffixes start with vowels.
Got it. Drop the E before a vowel suffix. What about unsaturation? Double or triple bonds?
Step 5. Indicate unsaturation. If the main chain has a double bond, change the ane ending of the parent name to -in. If it has a triple bond, change -ene to -ene.
So a 3-carbon chain with a double bond is propane-propene.
Exactly, propene. And with a triple bond.
Propane-propene.
Perfect, propene.
Okay, let's try a few more using propane, 3 carbons as the base, with a chlorine.
Chlorine uses the prefix chloro. So chloropropane, you'd also need a number to say where the chlorine is if the chain was longer, but let's keep it simple for now.
Okay. Alcohol.
Suffix ol starts with O.
Okay.
Drop the E.
Propanol.
Suffix ol starts with E.
Ketone, CO.
Suffix 1 starts with O. Drop the E.
Propanone.
Carboxylic acid, COA.
Suffix oic acid starts with O. Drop the E. Propanoic acid. And we did propene and propine. Wow, okay. It's systematic. Identify chain, identify functional group, apply suffix-prefix rules, adjust for saturation.
That's the core logic. It takes practice, but it allows for unambiguous naming.
Yeah.
Absolutely vital skill.
Right. Now that we can name them and understand their structure, let's get into their reactions. Chemical properties. You mentioned combustion first, since so many are fuels.
Exactly. Let's start with A. Combustion, burning. Carbon, in any of its forms, burns in oxygen. What does it produce?
Carbon dioxide and heat and light.
Correct. C plus O2 equals CO2 plus heat and light. Most carbon compounds, especially hydrocarbons, do the same thing. They burn readily in oxygen, releasing a lot of energy. It's essentially rapid oxidation.
So methane, CH4, burns to give.
CO2N, what else is in methane? So it also gives H2O, water, CH4 plus 2O2 plus 2H2O plus energy. You need to balance it, of course.
Okay. And ethanol, CH3CH2OH, it has CH and O.
Same product as combustion is complete. CO2 and H2O, CH3CH2OH plus 3O2 plus 3H2O plus energy. The oxygen in the ethanol itself contributes.
So complete combustion gives CO2 and H2O plus energy. What about the flame? You mentioned blue versus yellow flames earlier.
Ah, yes, flame characteristics, very practical. Saturated hydrocarbons like LPG methane usually burn with a clean blue flame if there's enough oxygen. That indicates complete combustion. Unsaturated compounds like oils or things with less hydrogen relative to carbon often burn with a yellow, sooty flame.
Sooty means black smoke. Why?
It indicates incomplete combustion. There isn't enough oxygen to convert all the carbon to CO2. So some unburnt carbon particles, soot, are produced. These tiny particles get heated up in the flame and glow yellow-hot, giving the flame its color, and then escape as smoke.
So a yellow flame means wasted fuel and pollution?
Pretty much.
Yeah.
Even saturated fuels will burn with a sooty flame if you limit the air supply. Think about a Bunsen burner. Close the air hole, you get a yellow smoky flame. Open it, you get a clean, hot blue flame.
Like the air vents on a gas stove. They get blocked, the pots get black.
Exactly. Blackened pots mean blocked air holes, incomplete combustion, wasted fuel.
And real fuels like coal and petrol aren't pure, right? They have impurities.
Yes, often nitrogen and sulfur compounds. When these burn, they form oxides of nitrogen, NOx, and sulfur.
Which cause acid rain and pollution.
Major environmental pollutants, absolutely.
Quick question, why do some things burn with a flame and others just glow?
Good one. Flames are only produced when gaseous substances burn. When you light wood, the volatile gases burn first, giving a flame. Charcoal, once the volatiles are gone, might just glow red as the solid carbon oxidizes on the surface without forming much gas to sustain a flame.
Ah, okay. Gas burns with a flame.
Oh.
Yes. And you mentioned coal and petroleum are fossil fuels formed from ancient life.
Yes, briefly. Coal comes from ancient trees and plants buried in swamps millions of years ago, compressed under heat and pressure. Oil and natural gas come from tiny marine organisms, plankton, algae, buried under sediment on the seabed, similarly transformed over geological time. They're literally fossilized energy.
Right, non-renewable. Okay, so combustion is one key reaction. What else? Oxidation.
Yes, B, oxidation. More controlled than combustion. A really important oxidation reaction you need to know is converting alcohols into carboxylic acids.
Ethanol to ethanoic acid.
Exactly. To do this, you need an oxidizing agent, a substance that adds oxygen or removes hydrogen. Key examples you must know are alkaline potassium permanganate, KMnO4, or acidified potassium dichromate, K2Cr2O7.
Okay, those strong oxidizing agents turn alcohols into acids. Got it. What's next? Addition reactions.
Yes. C, addition reaction. This is characteristic of unsaturated compounds. Those double and triple bonds can open up and add atoms across them.
Like adding hydrogen, hydrogenation.
Precisely. Adding hydrogen, H2, across a double or triple bond turns an unsaturated compound into a saturated one. But it doesn't happen on its own. You need a catalyst.
Catalyst speeds up the reaction but isn't used up.
Correct. Common catalysts for hydrogenation are metals like palladium, PD, or nickel, Ni.
And this is used industrially.
A hugely important application. Hydrogenation of vegetable oils. Vegetable oils like sunflower, soy, are typically liquids because they have unsaturated fatty acid chains with double bonds.
Healthier oils, usually.
Generally considered so. Animal fats are usually saturated, single bonds only, and solid. Hydrogenation uses hydrogen and a nickel catalyst to convert those liquid unsaturated oils into solid or semi-solid saturated fats. Think vanna, spotty ghee, or margarine.
So it makes liquid oils solid, but maybe less healthy.
That's the trade-off often discussed. Adds hydrogen, removes double bonds, changes physical properties. Very common exam topic.
Okay. Addition for unsaturated. What about saturated compounds? They're less reactive, you said? Do they react at all?
They do, but differently. They undergo desubstitution reactions. Saturated hydrocarbons are generally quite inert, but in the presence of sunlight, they react with halogens like chlorine, Cl2.
Sunlight is the key here.
Absolutely. The UV light provides the energy to initiate the reaction. What happens is a chlorine atom replaces or substitutes for a hydrogen atom on the saturated hydrocarbon chain.
So one atom swaps for another.
Yes. For example, methane, CH4, reacts with chlorine, Cl2, in sunlight. CH4 plus Cl2 E3Cl, chloromethane, plus HCl. A hydrogen is substituted by a chlorine, and this can continue, replacing more hydrogens if there's enough chlorine in light.
Okay. Substitution for saturated needs sunlight. Addition for unsaturated needs catalyst. Clear distinction.
Very clear, very important. Now, shall we zoom in on two specific, very important carbon compounds, ethanol and ethanoic acid?
Yes, definitely. They seem to come up everywhere. Let's start with ethanol.
Ethanol, CH3CH2OH, commonly called alcohol. It's the active ingredient in alcoholic drinks, of course.
Right. And used in medicines, too.
Yes, it's a good solvent. Used in tincture, iodine, cough syrups, tonics, and it mixes completely with water, infinitely soluble.
What about its effects? Consumption.
Important to know. Small amounts cause drunkenness, low metabolism, depressed nervous system, poor coordination. But even a small amount of pure ethanol, absolute alcohol, can be lethal. Long-term use causes serious health problems.
And what about methanol? CH3OH. That's different, right? Highly toxic.
Extremely dangerous. Even tiny amounts of methanol can cause death or blindness. In the liver, it's oxidized to methanol, formaldehyde, which is incredibly toxic. It damages cells, coagulates proteins, and specifically attacks the optic nerve.
That's scary. So how do industries prevent people from drinking industrial ethanol?
They use denatured alcohol. They add poisonous substances like methanol and often a dye like blue to make it unfit for drinking and easily recognizable. It's a safety measure.
Okay. Ethanol can also be used as fuel.
Yes. Sugarcane juice can be fermented to make ethanol. Some countries blend it with petrol, gasohol. It's considered a cleaner fuel because it burns to produce mainly CO2 and water, potentially less polluting than pure petrol.
Interesting. Now, what about its chemical reactions? You mentioned it reacts with sodium?
Yes, reaction 1. Reaction with sodium. Alcohols react with active metals like sodium. What gas is produced?
Hydrogen gas. Like acids with metals.
Exactly. Hydrogen gas, H2 bubbles off. This is a characteristic test for alcohols. The other product is sodium methoxide, CH3CH2ONA. So 2NaS plus 2CH3CH2OH, ACH3CH2AMX plus H2.
Okay. Produces hydrogen with sodium. What other key reaction? Dehydration.
Yes. Reaction 2. Dehydration, removing water. If you heat ethanol strongly around 443 K, 170 degrees, with excess concentrated sulfuric acid, H2SO4.
Sulfuric acid acts as the dehydrating agent, pulls water out.
Precisely. It removes the water molecule from ethanol, leaving behind the unsaturated hydrocarbon, ETH2CH2. So CH3CH2HU, CH2 plus H2O with hot conc, achieves H2SO4, converts an alcohol to an alkene.
Two key reactions. Forms H2 with Na, forms ethene with hot conc.
Yeah.
H2SO4. Got it. Now on to ethanoic acid.
Ethanoic acid, CH3COH, commonly known as acetic acid. It's a carboxylic acid.
Vinegar.
Yes, a dilute solution, 5 to 8% in water, is vinegar, used as preservative. Pure ethanoic acid has a melting point of 290 K, about 17 degrees C.
It can freeze in winter.
It often does in cold climates, which is why pure ethanoic acid is sometimes called glacial acetic acid. It looks like ice.
And it's an acid, but you said it's a weak acid, unlike HCl.
Very important distinction. Yes, it's a weak acid. Mineral acids like HCl ionize completely in water. Carboxylic acid like ethanoic acid only partially ionize, releasing fewer H+ ions. This difference in strength is crucial.
Okay. Weak acid. What are its key reactions? Esterification sounds important.
Reaction 1, esterification. Esters are formed when a carboxylic acid reacts with an alcohol, usually in the presence of an acid catalyst, like conc, H2SO4.
Acid plus alcohol, ester plus water.
Correct. So ethanoic acid plus ethanol, ethyl ethanoate ester plus water, CH3COH plus TH3CH2OH, CH3CH2CH3 plus H2O.
And esters are known for?
Their smell. They often have pleasant, fruity smells used in perfumes and flavorings.
Okay. And what's saponification? Is it related?
It's essentially the reverse reaction, but using a base. If you treat an ester with a strong alkali like sodium hydroxide and AOH and heat it, you get back the alcohol and the sodium salt of the carboxylic acid.
Why saponification?
Because this exact reaction is used to make soap. Soaps are sodium or potassium salts of long-chain carboxylic acids, fatty acids, made by hydrolyzing fats or oils, which are esters, with alkali.
Esterification makes esters. Saponification breaks them, using base, and makes soap ingredients. Got it.
Reaction 2. Reaction with a base. Being an acid, ethanoic acid reacts with bases like NaOH in a simple neutralization reaction.
Acid plus base as salt plus water.
Exactly. NaOH plus CH3COH, CH3CON, sodium ethanoate, the salt, plus H2O.
Soda neutralization. Okay. What about carbonates, like baking soda?
Reaction 3. Reaction with carbonates and hydrogen carbonates. Ethanoic acid reacts with sodium carbonate, NO2CO3, or sodium hydrogen carbonate, NHCO3, baking soda. What gas do acids usually produce from carbonates?
Carbon dioxide, CO2, causes fizzing.
Correct. You get the salt, sodium ethanoate, water, and CO2 gas. 2CH3COH plus NaClCOH plus H2O plus CO2.
And we can test for that CO2.
Yes, the classic test. Bubble the gas through lime water, calcium hydroxide solution. If CO2 is present, the lime water turns milky or cloudy due to the formation of insoluble calcium carbonate. Essential test to know.
Okay, ethanoic acid. Weak acid, forms esters, neutralizes bases, gives CO2 with carbonates. Seems straightforward.
Good summary. Now, finally, let's use some of this chemistry to understand something very practical. Soaps and detergents. How do they actually clean?
Yes. You mentioned saponification makes soap ingredients.
Right.
So how does soap tackle oily dirt if oil and water don't mix?
It all comes down to the unique structure of the soap molecule itself. Remember, soaps are sodium or potassium salts of long-chain carboxylic acids.
Long chains. Okay.
Think of the molecule having two distinct ends, a dual nature. One, the long hydrocarbon chain, the tail. This part is hydrophobic, water-hating, but it's lipophilic, oil-loving. It readily dissolves in oil and grease. Two, the ionic end, the head, usually CO0 plus Q. This part is hydrophilic, water-loving. It readily interacts with water molecules.
So someone likes oil, the other one likes water, a double agent.
Kind of. Now imagine oily dirt on fabric, surrounded by water with soap dissolved in it. What happens?
The oil-loving tails bury into the dirt.
Exactly. The hydrophobic tails dive into the oil droplet, while the hydrophilic heads stay pointing outwards, remaining in contact with the water.
So the oil droplet gets surrounded by soap molecules. Tails in, heads out.
Precisely. As more soap molecules cluster around the dirt, they form a spherical structure called a micelle. The oily dirt is trapped inside the hydrophobic core, and the outside surface is covered with the water-loving hydrophilic heads.
Ah. So the micelle traps the dirt inside, but its outside can mix with water.
Yes, it forms an emulsion, tiny droplets of oil with dirt suspended in water, stabilized by the soap molecules. The micelle effectively lifts the dirt off the surface and carries it into the water.
Clever. And how does rinsing wash it away?
The micelles stay suspended in the water as a colloid. They don't clump together because their outer surfaces are negatively charged, those COO heads, and like charges repel each other. This repulsion keeps the micelles dispersed, allowing the trapped dirt to be easily washed away with the rinse water.
So that's why soap solutions look cloudy, the micelles scattering light.
That's the Tyndall effect, yes. And why do we need to scrub or agitate clothes?
To help dislodge the dirt and mix the soap around so it can form micelles.
Exactly. Agitation helps the process along.
Okay, that makes sense. But what about hard water? Soap doesn't work well, right? It forms scum.
Correct. Hard water contains dissolved calcium, K2+, and magnesium, Mg2+ ions. Soap molecules react with these ions.
Instead of forming micelles.
They react to form an insoluble precipitate, that sticky white stuff called scum, calcium stearate or magnesium stearate, for example. This scum doesn't clean, and it wastes soap because the soap is reacting with the hard water ions instead of the dirt.
So you need more soap and hard water. Okay. How do detergents solve this?
Detergents are chemically different. They're often sodium salts of long-chain sulfonic acids or other variations. They also have the hydrophobic tail and hydrophilic head structure.
But the head is different.
Yes, the charged head group is different. For example, a sulfonate group, aniso3 Na+. And crucially, the calcium and magnesium salts of these detergent molecules are soluble in water.
Ah, so they don't form insoluble scum with K2+ and Mg2+ ions.
Exactly. Detergents remain effective cleansing agents even in hard water because they don't precipitate out. They can still form micelles and wash away dirt without forming scum.
That's why they're used in laundry powders and shampoos. They work everywhere.
Generally, yes. They maintain their effectiveness in hard water. So, quick test. Soap lathers well in soft water but forms scum in hard water. Detergent lathers well in both.
Brilliant. Soap versus detergent, micelle action, hard water problem solved. That covers a lot.
It certainly does. We've journeyed all the way from carbon's basic properties to its complex bonding, its amazing versatility through catenation and tetravalency, the different forms like diamond and graphite.
Looked at saturated versus unsaturated, isomers, functional groups, naming them systematically.
And covered key reactions like combustion, oxidation, addition, substitution. We dove deep into ethanol and ethanoic acid, their properties and reactions.
And finished with the practical chemistry of how soaps and detergents work, including micelle formation and the hard water issue. A really thorough deep dive.
I hope it provided clarity on these core concepts.
Definitely. It was incredibly clear, Guruji. Expert speaker. My understanding, especially of the bonding, the reactions, and why carbon is so unique, feels much stronger now. The step-by-step approach and the examples really help cement it for exams. Thank you.
Excellent. That's the goal. But remember, understanding is the first step. Mastery comes with practice.
Right.
So my advice is definitely revise this chapter again. Pay close attention to the different reaction types, the conditions needed for each catalyst, temperature, sunlight, and crucially, practice past exam questions on this topic.
Well,
That's how you'll really solidify your knowledge and identify any areas you need to revisit. If any doubts come up while you're practicing, don't hesitate to seek clarification. Keep putting in the effort, keep learning, and you'll do great.
thanks very much. That was incredibly helpful.
My pleasure.